Imagine you have a number like 3.7. The fractional part is just the 0.7, the little extra bit after you take away the whole number 3. We write it with curly braces, like this, 3.7. That means the fractional part of 3.7. And here's the key rule: the answer is always 0 or bigger, but always less than 1. So, 3.7 is 0.7. 5.0 is 0. 9.99 is 0.9. It's the piece of the number that lives between the whole numbers on the number line. Why do we care about this little leftover piece? Because it captures what repeats. Think of a clock. When the minute hand goes past 60, it doesn't keep counting 61, 62, it wraps back to 1. The fractional part does exactly that. It ignores how many whole cycles have passed and just tells you where you are inside the current cycle. On a number line, every whole number is like a new lap. The fractional part is your position on that lap. This idea is everywhere in math, in waves, in signals, in anything that repeats. It's the heart of what we call a periodic function, and it's a building block you'll see again and again in calculus. So how do we actually get the fractional part? We need a way to chop off the whole number. That tool is called the floor function, written with these funny L-shaped brackets. The floor of a number is the greatest integer less than or equal to it. Basically, you just drop the decimal. Floor of 3.7 is 3. Floor of 5 is 5. Floor of negative 1.2 is negative 2, because negative 2 is the next integer down. Once you have the floor, the fractional part is simply the original number minus its floor. For 3.7, 3.7 minus 3 gives 0.7. That's it. And because the floor is always the integer just below or equal to x, the difference is always at least 0 and strictly less than 1. Let's use this to solve a real problem. Suppose you're turning a wheel and you measure the total angle it has spun, 400 degrees. But you only care about its final position, which is always between 0 and 360 degrees. This is exactly the fractional part idea. First, divide the angle by 360 to get the number of full turns. 400 divided by 360 is about 1.1. The floor of that is 1, that's the 1 full turn. The fractional part is 1.1 minus 1, which is about 0.1. Multiply that back by 360 and you get 40 degrees. So after spinning 400 degrees, the wheel ends up at 40 degrees. The fractional part just stripped away the whole turn. And that's the whole idea. The fractional part tells you where you are inside the current cycle, no matter how many cycles came before. You already know that the fractional part, written with curly braces, is what remains after you take away the integer part. For example, the fractional part of 2.3 is 0.3. Now we want to see this as a picture, a graph. We put x on the horizontal axis and y, which equals the fractional part of x, on the vertical axis. What we get is a repeating pattern that looks like the teeth of a saw, rising from 0 to almost 1, then dropping back to 0 and starting again. That's why it's called a sawtooth wave. Why do we care about drawing this graph? Because it reveals a special kind of repeating behavior. The pattern repeats exactly every time x increases by 1. We say the function is periodic, and its period is 1. This is a big idea in calculus, understanding how a function behaves as x gets close to an integer, where the graph suddenly jumps. Those jumps are called discontinuities, and they are central to the study of limits and continuity, which you'll need for the IIT-JEE. Seeing the graph makes these abstract ideas concrete. Let's build the graph step by step. First, look at x between 0 and 1. The integer part of any number here is 0, so the fractional part is just the number itself. That means y equals x. It's a straight line from 0 up to 1, but at exactly x equals 1, the fractional part drops to 0, so we put an open circle at the top to show it doesn't include that point. Now move to x between 1 and 2. The integer part is 1, so the fractional part is x minus 1. This gives another straight line, starting at 0 when x is 1, with a closed dot, and going up to almost 1 at x equals 2, where we again put an open circle. This pattern, a line segment of slope 1, open at the right end, closed at the left, repeats for every integer interval. Let's use the graph to solve a concrete problem. Suppose you need the fractional part of 2.7. On the graph, find 2.7 on the x-axis. It lies between 2 and 3. Go straight up to the slanted line. That line represents y equals x minus 2, because the integer part is 2. Now read across to the y-axis. You'll see it's about 0.7. We can verify 2.7 minus 2 is indeed 0.7. The graph gives you a quick visual way to find fractional parts. And notice the open circle at 3, if x were exactly 3, the y value would be 0, not 1. This method works for any number, just find its interval and read the height. Imagine you're walking along the graph of the fractional part function, which we already know looks like a sawtooth wave. You're heading toward x equals 2. A limit is simply the y value the function is aiming for as you get closer and closer to that x, even if you never actually step on it. But here's the catch, you can approach from the left, with x values like 1.9, 1.99, 1.999, or from the right, with 2.1, 2.01, 2.001. The left-hand limit is what the function heads toward from the smaller side, and the right-hand limit is what it heads toward from the larger side. The full, two-sided limit only exists if both of these one-sided limits agree on the same destination. Why do we care so much about limits? Because they tell us whether a function is well-behaved and smooth, or if it has sudden breaks. Think of a staircase versus a ramp. A ramp is smooth, you can slide your hand along it without any surprises. A staircase has abrupt jumps. Limits are the tool that lets us detect those jumps mathematically. For the fractional part function, we already know it has a sawtooth shape with sharp drops at every integer. Limits will let us prove that those drops are real breaks, not just visual tricks. This idea of a function being a continuous, having no breaks, is the bedrock for everything that comes next in calculus, like finding the slope of a curve, because you can't find a slope at a broken edge. Let's see exactly how this works for our fractional part function at x equals 2. First, the left-hand limit. We put our finger on the graph at x equals 1.5, where the value is 0.5, and slide right. As we get to 1.9, the value is 0.9, at 1.99, it's 0.99, at 1.999, it's 0.999. The function is climbing a straight ramp, heading straight for a value of 1. So the left-hand limit is 1. Now the right-hand limit. We start at x equals 2.5, value 0.5, and slide left. At 2.1, value is 0.1, at 2.01, value is 0.01, at 2.001, value is 0.001. The function is on a different ramp, heading straight for 0. The two one-sided limits are 1 and 0. They don't match, so the two-sided limit does not exist. A function is continuous at a point only if the limit exists and equals the function's actual value there. Let's solve a concrete problem, determine if the fractional part function is continuous at x equals 2, and if not, describe the break. We already did the legwork. The left-hand limit, coming from values like 1.999, gives us 1. The right-hand limit, coming from 2.001, gives us 0. Since 1 and 0 are different, the two-sided limit does not exist. The function's actual value at x equals 2 is the fractional part of 2, which is 0. So the function is not continuous there. This specific type of break, where the left and right limits are finite but different, is called a jump discontinuity. You can literally see the function jump from a value of 1 down to 0 at the integer. This happens at every single integer for the fractional part function, because the sawtooth pattern resets. So the function is continuous everywhere except at integers, where it has these jump discontinuities. A derivative measures how steep a function is at a single point. Think of it as the slope of a microscopic tangent line touching the graph. For the fractional part function, which we already know looks like a sawtooth wave, the graph between integers is just a straight diagonal line. On any open interval from n to n plus 1, the function is simply x minus n, a line with slope 1. But right at the integer points, the graph has a sharp drop, a jump discontinuity, so there is no single tangent line you can draw. The slope is undefined there. Knowing the derivative tells us how fast the fractional part is changing. Since the slope is 1 almost everywhere, the function grows at a steady rate of 1 unit per unit, just like the function f of x equals x. But the jumps at integers mean the function isn't smooth there. This leads to an important idea: a function can be differentiable almost everywhere, meaning everywhere except a few isolated points. For the sawtooth, those bad points are just the integers, which are spaced out and don't ruin the overall behavior. Let's derive this step by step. Pick any integer n, and look at the open interval between n and n plus 1. For any x in that interval, the floor of x is just n, so the fractional part is x minus n. The derivative of x is 1, and the derivative of a constant n is 0, so the slope is exactly 1. Now at the integer itself, the story changes. Just to the left, the function is coming from x minus n minus 1, which has slope 1, but the right-hand limit of the slope is also 1. Wait, let's be precise. The left-hand derivative uses the line from the previous piece, which is x minus n minus 1, so its slope is 1. The right-hand derivative uses x minus n, also slope 1. But the function jumps, so the graph has a corner with no tangent. The derivative doesn't exist because the function isn't continuous there. Let's solve a concrete problem. Suppose we want the derivative of the fractional part function at x equals 2.5. First, identify which interval it's in. 2.5 lies between 2 and 3, so n is 2. On this interval, the function is x minus 2. The derivative of x minus 2 is simply 1. So the slope at that point is 1. Now what about at x equals 3? 3 is an integer, a jump point. The function isn't continuous there, so the derivative does not exist. This method works for any non-integer. Just find n, write the function as x minus n, and differentiate to get 1. At integers, the derivative never exists because of the jump. A definite integral is just the signed area trapped between a graph and the x-axis, from a starting x to an ending x. For our sawtooth function, the fractional part of x, one period runs from 0 to 1. The graph is a straight line climbing from 0 to 1, so the shape underneath is a right triangle. Its base is 1 unit wide, its height is 1 unit tall. The area of any right triangle is half the base times the height, so this area is exactly 1/2. That single number is the integral of the fractional part over one full period. Why do we care about the area under a sawtooth? Imagine the graph represents a repeating ramp, like the height of a factory machine's cutter as it cycles. If you want the total material removed over many cycles, you need to add up the area under the curve. The integral gives you exactly that accumulated total. It also lets you find the average height over time, which is just the total area divided by the length. And once you can integrate over one period, you can handle any interval by chopping it at the integer breakpoints. This is the bridge between the graph shape and a new function, the antiderivative, that tracks the running total area. Here's how we actually compute it. The fractional part function repeats every integer, so to integrate from 0 to some number like 3.7, we snap the interval at the integers 0 to 1, 1 to 2, 2 to 3, and 3 to 3.7. Each full period is a right triangle of area 1/2. The leftover piece from 3 to 3.7 is a smaller right triangle, base 0.7, height 0.7, area half of 0.7 squared. We just add up all the full triangles plus the partial one. This adding up process builds the antiderivative, a function that gives the accumulated area from 0 to x. Its formula is a piecewise quadratic. For x between 0 and 1 it's x squared over 2, for larger x, it's the number of full periods times 1/2 plus the leftover triangle area. Let's solve a concrete problem. A cutting tool's depth follows the fractional part function, 1 unit deep per cycle. After 4.3 cycles, how much total material has been removed? The area under the graph is the total cut. For full cycles each contribute an area of 1/2, so that's 2 square units. The remaining 0.3 of a cycle is a tiny right triangle with base 0.3 and height 0.3. Its area is half of 0.3 squared, which is half of 0.09, or 0.045. Adding them gives 2.0 for 5 square units. This method works for any number of cycles, just count the full triangles and add the partial one. So the whole idea is, the integral of a periodic piecewise linear function is just the sum of simple triangle areas. Imagine a wheel spinning. Every time it completes one full turn, its angle goes back to 0 and starts over. That is wrapping, taking any big number and squeezing it into a fixed range, like 0 to 360 degrees. A digital clock does the same thing. After 59 seconds, the second's digit resets to 0, and the minute ticks up. The fractional part function we already know is the engine behind this. It strips away whole cycles, leaving only the leftover fraction, exactly what we need to model anything that repeats and resets. Why do we care about wrapping? Because the world is full of cycles. A Ferris wheel seat goes up and down and comes back to the start. Sound waves vibrate back and forth. Even the time on your phone repeats every 12 or 24 hours. Without wrapping, an angle like 720 degrees would mean nothing visually, it is just 2 full circles. Wrapping it to 0 degrees tells us exactly where the wheel actually points. In electronics, this wrapping creates a sawtooth wave, a signal that ramps up linearly, then snaps back to 0 and ramps again. That wave is a building block for synthesizers, digital clocks, and all of signal processing. Here is how wrapping works, using the fractional part we already understand. Take any number, like 7.3. The floor function gives the integer part, 7 whole cycles. Subtract that, and the fractional part is 0.3. That is the leftover after all complete cycles are removed. To wrap an angle into 0 to 2 pi, we first divide the angle by 2 pi to count how many full turns fit. The fractional part of that division tells us what fraction of a turn remains. Multiply back by 2 pi, and we have the wrapped angle. In programming, this is the modulo operator. A mod b means the remainder after dividing a by b. It is exactly the fractional part of a over b, scaled up by b. The sawtooth wave is just the fractional part of time, growing linearly and snapping at every integer. Let us solve a concrete problem. The digital clock shows only the seconds part. If 125 seconds have passed since the clock started, what number does the seconds display show? The clock wraps every 60 seconds. So we take the total time, 125, divide by 60 to count the cycles. That gives about 2.083. The integer part, 2, means 2 full minutes have passed. The fractional part, 0.083, is the fraction of the current minute. Multiply by 60 to get the seconds, 0.083 times 60 equals 5. The display shows 5 seconds. This is exactly the fractional part function at work. The same method finds the phase of a wave, the angle of a rotating wheel, or the remainder in any programming loop. Let's step back and see the whole picture. The fractional part function, written as curly braces around x, is simply x minus the floor of x. The floor of x is the greatest integer less than or equal to x, the integer part. So the fractional part is whatever is left over after you take away that integer. Visually, it's a sawtooth wave. It ramps up from 0 to just below 1, then drops back to 0 and repeats. Every time x hits a new integer, the floor jumps up by 1, so the fractional part resets. This one simple idea, splitting a number into its integer and fractional pieces, gives us a function that is periodic, piecewise linear, and full of interesting calculus behavior. It's like a heartbeat that ticks every second, always returning to the same pattern. Why do we care so much about this jagged little function? Because the world is full of cycles that reset. Think of the second hand on a clock. It sweeps from 0 to 60, then snaps back to 0. The fractional part captures exactly that idea. It tells you where you are inside the current cycle, your phase. If you multiply the fractional part by the length of a cycle, you get the exact position within it. This is the mathematical heart of any repeating phenomenon, the daily rotation of the Earth, the oscillation of a pendulum, the phase of a wave. In signal processing, every waveform that repeats can be built from or analyzed using this basic resetting pattern. The fractional part is the simplest periodic function, and understanding its calculus opens the door to understanding the calculus of all periodic functions. Now let's see how calculus works on this function. First, the derivative. Between integers, the graph is a straight line with a slope of 1. So the derivative is 1 almost everywhere. But at the exact integer points, there's a sharp corner, a jump discontinuity in the function itself. The left-hand limit as you approach an integer is 1, but the right-hand limit is 0. Because these don't match, the derivative doesn't exist at those points. We say the function is differentiable almost everywhere. Next, the integral. To find the area under the sawtooth, we can just add up the areas of the triangles. Each tooth from an integer n to n plus 1 is a right triangle with a base of 1 and a height of 1. Its area is 1/2. So the definite integral from 0 to any integer is just the number of teeth times 1/2. For non-integer limits, we add the area of a trapezoid. Let's ground all this in a real example. Imagine a bicycle wheel with a reflector on one spoke. As the wheel spins, the height of the reflector goes up and down in a repeating pattern. If we want to know the reflector's vertical speed at any moment, we're taking a derivative. The height function is smooth and wave-like, so its derivative exists everywhere. But now imagine we want to model just the phase of the wheel, how far along the current rotation we are, from 0 to 1 full turn. That's exactly the fractional part function. The phase ramps up linearly, then resets. Its derivative is the constant angular speed, except at the reset points where it's undefined. If we want the total phase accumulated over several turns, we integrate. The area under the phase curve gives us the total angular distance. By breaking the integral at the reset points, we can handle the discontinuities cleanly.